Yoshiki Eto about his research on the development of a new HIV vaccine. Presentation.
My name is Yoshiki Eto. I'm a PhD student in University of Barcelona. I'm originally from Japan. I studied pharmaceutical sciences in the University of Kyoto in Japan. And then I moved to the United States. Then I did my master's in molecular microbiology and immunology at Johns Hopkins University.
How do viruses survive?
Viruses can't really survive by themselves. That's true. Then they need to use our system to amplify. In case of bacteria or parasite, they can survive by themselves. They can make their energy by themselves, but it's like a virus need to use our bodies.
HIV virus specifics.
First of all, it is RNA virus, so it has high mutation rate compared to DNA virus. Normally, if you get the infection of a normal virus, you are gonna basically eliminate thanks to your immune systems. But in case of HIV, you cannot eliminate from your body. Sleeps hibernate inside the immune cells, can stay and can wake up at some point. Also, because of these mutations, our immune system cannot recognize as enemy. They can escape from our immune system.
Treatments in development.
One of them, preventive HIV vaccine. The other one is therapeutic AIDS vaccine.
How do vaccines work?
Classic vaccines are basically two types. One of them is basically live attenuated vaccine. It means the virus, but it's weaker version. But you can develop immunity enough to defend yourself against the virus. Or inactivated virus, it means it's dead virus.
Why is it so difficult to develop an HIV vaccine?
But in case of HIV, we cannot really use these two vaccines. Why? After you get the infection, the virus stay in our body. We never ever eliminate
Vaccine
With
inactivated virus.
Inactivation usually works at 99.9%. Then, if it is like
Virus.
0.001% or whatever, if it remains, it could stay in our body. Then sometimes, basically, so as I said, we cannot really get rid of this virus completely from our body by our immune system. So it's really dangerous to use this inactivated vaccine as well.
New types of vaccines.
So what they are using is capsid protein. It means a shell of virus. We can produce this only shells, but it doesn't contain any DNA, so it can't replicate. It's not infectious. Just only shells. For example, let's say this is a water bottle. Then basically some cells can produce just only plastic part, but not water part. So, but our body can recognize this bottle as an enemy, as a virus, then can produce antibodies, for example.
Virus-like particle PLV vaccines.
Shells, but it doesn't contain anything inside. It's called a virus-like particle because it's a virus-like particle, but it's fake. It's not a virus.
RNA, DNA vaccines for HIV.
Has been tested, but they are not successful in some studies. Basically, usually placebo group is basically get much more HIV infection than vaccinated group. That's an ideal situation, but in case of some studies, it happened vice versa. The people who got the HIV vaccine candidate got much more HIV infection than placebo group. We don't really know why. I mean, our human bodies are complicated, not always like react as we expect.
What is your research project about?
My project, I'm using HPV virus-like particle as a basically like a tool because it's already in market. Then I'm adding HIV epitope, part of HIV on this virus-like particle so that our body can recognize this epitope, HIV, part of HIV. My project is core of the virus-like particle is HPV, human papillomavirus. Then on the human papillomavirus, I'm adding small part of HIV. So, but there's another vaccine. I mean, it's not vaccine yet, but it's under development. It's HIV virus-like particle. So it looks like HIV. It's totally different from mine. It looks like HIV, but inside it doesn't contain any genetic materials from the HIV.
Plans after your PhD?
So after my PhD, of course I would like to continue, but you never know. It depends on the funding. Funding, like it's like a wave.